Hi everyone, welcome to today's video. In this video, we're going to be talking about an adiabatic flame temperature and how to calculate it. So when we want to start thinking about this, we have some system, or you can think of it as a container, and this container will take in air and fuel. And for this example, it will be at a temperature of 298 kelvins. And once it goes through a full combustion process, it will produce a flame that will come out at a much higher temperature that we'll call T. So this will be a steady state process, meaning that the mass that's coming in will be equal to the mass that's going out. It will also not have any changes in kinetic energy, potential energy, work, heat, etc., which means it's also adiabatic. So there exists such a thing known as an adiabatic flame temperature, which is how hot the flame is that is produced from the combustion of air and fuel, that has no change in heat or energy. This is within steady state. Okay. Hi everyone, welcome to this video. Today we'll be talking about an adiabatic flame temperature and how to calculate it. So let's start with having a container or a system that will take in air and fuel at a temperature of 298 Kelvin. This air and fuel will go into the system and go through a full combustion process, and then produce a flame at a temperature much higher than our starting point, and we can call that temperature T. So this process will be steady state, meaning that the mass coming in will be equal to the mass going out, and there will also be no heat loss or gain to or from the environment, and changes in kinetic energy, potential energy, and work are negligible. So it's also adiabatic. And so there is such a thing known as an adiabatic flame temperature, which is essentially how hot a flame is that is produced from air and fuel that go through a full combustion process, with negligible changes in kinetic energy, potential energy, and heat. And so since it's a steady state process, we know that the enthalpy in times the change in mass coming in is equal to enthalpy going out times the change in mass going out. But as I mentioned, the mass coming in and going out will be the same. So we're just left with enthalpy in is equal to enthalpy going out, and this is just a confirmation that this process is also adiabatic. So with this, we have to account for the change in temperature, because this isn't something simple like heating up water. If it was, we would just be able to multiply it by a constant heat capacity. But since this flame will come out at a temperature much higher than the temperature that we start with, we have to multiply this by a heat capacity with respect to the change in temperature, and integrate that and include the heat of formations. So we have the heat of formation at temperature T, which is our very high flame temperature, is equal to the heat of formation at our initial temperature, which is 298 kelvins, plus, and then we have to integrate our heat capacity starting at 298 to T, which is the heat capacity at constant pressure with respect, or times the change in temperature. And so for the heat capacity, we're going to be using an equation known as a ChemCAD equation 107. And then we'll go over and take a look at that. So this is ChemCAD equation 107, where y equals a plus b times c over t divided by hyperbolic sine of c over t all squared, plus d times e over t divided by hyperbolic cosine of e over t all squared. And we're going to need to integrate this, and we should be able to do that pretty easily with the constant a, because once we integrate it, it'll just be a times t. But for the terms that include b, c, d, and e, it'll be much harder because this isn't a simple integration to do. So we're going to go to Wolfram alpha and do the integration there. So we have the integral c over t divided by hyperbolic cosine of c over t, and then all of that is squared, and we have to take that with respect to t. And that gives us c times the cotangent, the hyperbolic cotangent of c divided by t. And so for the d, the term that has d in it, we just have to replace the c with e, and multiply e over t by hyperbolic cosine. E instead of c, cosine instead of sine. And this gives us negative e times hyperbolic tangent of e over t. And it's important to mention that this e is not the function e that is typically used in calculus and other kinds of math. It's just the variable e that we had in the ChemCAD equation. And so now we can go back to the board for the stoichiometric balance of our fuel. We can begin balancing the reactants and products from our combustion of fuel and air. So our fuel is going to be made up of methane, ethane, and N-propane, where methane is CH4, ethane is C2H6, and N-propane is C3H8. So a typical combustion process would be to take our beginning compounds and burn them with oxygen, and as a result we'll get carbon dioxide and water. But we aren't burning these compounds with pure oxygen. Instead, we're burning them with air, and air has a makeup of basically 79% nitrogen and 21% oxygen. And this also means it is 0.79 moles of N2 and 0.21 moles of O2. So since we're burning with air, we have to account for nitrogen. So we can write this reaction as such for all three. And so we have to balance these reactions, because what we start with on the left has to be what we end with on the right. So starting with methane, basically how we'll go is I'll just see how many atoms we have on the left and then compare it to the right and adjust so that the amounts of each are equivalent. So since we have one carbon in methane and no other carbons on the left, we need to have one carbon on the right, which we do. For hydrogen, there's 4 on the left, but there's only 2 on the right, and water, so we have to multiply this by 2 so that we end up getting 2 times 2, 4 hydrogens. So then our hydrogens are equal. But then we get to the oxygens, and we see that we have 2 oxygens on the left, and we have 2 oxygens on the right in the carbon dioxide, but then 2 more oxygens on the right in the water, since we just multiplied the water molecule by 2. And since there are 4 oxygens on the right, we need to make it equal 4 oxygens on the left, and since we already have 2, we can multiply our oxygen molecule by 2. And as for our nitrogen, well, we don't really know how much nitrogen we would need to start out with and burn, but we do have the ratio of air, which is 79 to 21 of nitrogen to oxygen. So in order to only end up with nitrogen, we can first multiply it by the number of starting moles of oxygen we have, which is 2. And then we have to multiply it by the molar ratio, which is 79 over 21. On both sides. And so then we follow this process all the way through. There's 2 carbons on the left, 1 on the right, multiply it by 2. We have 6 hydrogens on the left, 2 on the right, so we multiply this by 3. There's 2 oxygens on the left, but there's 4 in carbon dioxide and 3 in water, so we have 7 oxygens on the right. So to get 7 on the left, we have to multiply this by a fraction of 7 over 2. And then for nitrogen, well, we have to multiply nitrogen by the amount of oxygen we have, which is 7 over 2. And then we have to multiply this again by our ratio of air, which is 79 over 21. And finally, in propane, we have 3 carbon dioxide on the left, 1 on the right, so we multiply it by 3. 8 hydrogens on the left, 2 on the right, so we multiply it by 4. 2 oxygens on the left, we have 6 in carbon dioxide and 4 in water, so we have 10 on the right, so we multiply this by 5. And then we have to multiply our nitrogens by 5, and then multiply them by the ratio once more, 79 over 21. And so this is the stoichiometry and the balance for our fuel. And so it's also worth noting that because we are burning these compounds with air rather than pure oxygen, the temperature of the flame would be less compared to burning it with pure oxygen, because it takes energy to heat up this nitrogen as well. So now that we've done this, we can start coding this in Collaboratory. So to start coding this, I've already taken a couple steps beforehand by importing a GitHub module called CHE Tools, which holds a lot of important data for chemical compounds. And I've also imported NumPy, SciPy Optimize for our root solver, and tools.che, which allows us to pull the data from the module and actually use it within our code. So we can actually take a look by going into CHG tools and data and taking a look at ethane and seeing all of the data that is here. But we're specifically going to be worried about the ideal gas heat of formation, and we should see that it's in joules per kilomole. So we'll have to divide that by 1,000 to make sure that we get it in joules per mole. And then the other thing that we'll be really concerned with is the ideal gas heat capacity, because this relates to our ChemCAD equation 107, as you can see here. And we're going to worry about these coefficients, because these coefficients are what correlates to the variables within equation 107, A, B, C, D, and E, and those are listed here. So first, we're going to want to call forth the properties of the chemical compounds that we used. So we're going to do CHE props, and then we're going to do methane, ethane, and propane, oxygen, nitrogen, carbon dioxide, and water. So next, we're going to want to create a matrix for the number of carbon and hydrogen atoms within our starting materials of our fuel, which is methane, ethane, and propane. So we can do fuel formula is equal to 1 carbon, 4 hydrogen for methane, 2 carbon, 6 hydrogen for ethane, and 3 carbon, 8 hydrogen for in propane. And then we're going to want to create another matrix for our moles of the starting components, methane, ethane, and propane. So we'll do N fuel is equal to, we'll start with 10 moles of methane, 1.5 moles of N propane, of ethane, and 1 mole of N propane. And then to get the moles of carbon and hydrogen for each of these, we will simply create a dot product between these two matrices or arrays. So we can do the moles of carbon and the moles of hydrogen is equal to fuel formula. Formula at N fuel. And then next, we're going to want to have the moles of carbon dioxide. So that's NCO2, and that's equal to just the moles of carbon. And then after that, we want to do the moles of water. And that's equal to the moles of hydrogen divided by 2. And then for our moles of oxygen, it'll be the moles of hydrogen plus the moles of carbon dioxide divided by 2. And then it's the moles of water. And then for the moles of nitrogen, since it's not pure air, and nitrogen is a very big component of air. I'm sorry, it's not pure oxygen that we're burning up with, it's air, and nitrogen is a big component of the air since it's 79% of it. So we have to do the ratio of nitrogen to oxygen within air, which is 79 divided by 21, and then multiply that by the moles of oxygen. Okay. So from here, we can start calculating the moles of our fuel, or excuse me, the moles of our feed going in and the moles of our products coming out. So we can do this by starting with in feed is equal to, and we need to be able to combine our matrices or our arrays. So we're going to use np.concatenate to do that. And we'll start with in fuel, and then we have to do np array, and this has to be in the order that we did it in. So started with oxygen, so it'll be NO2, and then in N2, and since it's our feed, we don't have any carbon dioxide or water, so it'll be 0, 0, 0, 0. And then for our products, it can be the same thing. Except we'll want to make all of the numbers within in fuel equal to 0, since we will have none of that left after the combustion finishes. So we can do np dot zeros like in fuel, and that'll just make it so you can put in any amount of compounds that don't necessarily have to be methane, ethane, and propane, and still be able to apply it to this equation. And so our moles of oxygen will be gone. We'll still have nitrogen, and then it'll be NCO2 and NH2O. So now we can use our ChemCAD equation 107, and this is actually going to, give us the heat of formation at the chosen temperature. So we can define, and this is also, that's going to be our sensible heat. So we can define delta H sens for a sensible heat, for ideal gas at T, and then return. And this is just the integrated chemical equation that we did using Wolfram alpha. So we'll do P and then heat capacity, Cp, ideal gas, and then A, because that was our first constant. And we can copy this and then just put in the correct constant for each term. So we have to multiply this by the temperature plus the same thing for B times that for C, but we divided this by the hyperbolic tangent of C divided by T. And then this is minus heat capacity times D, also times E, and then also times the hyperbolic tangent of that, same thing for E divided by T. I think I'm missing a parenthesis. Oh, okay. No, we're good. And then we have to divide it by 1,000 because we need it to be in moles. And as I mentioned earlier, the heat of formation is in kilomoles. So now we have to calculate the heat of formation at the final temperature. And if you remember, that's just equal to the heat of formation at our initial temperature plus the integrated heat capacity from the initial temperature, 298 kelvins, to the final temperature. So we can define this function, and we'll do heat of formation of ideal gas, but HFIG is already a function, so we'll just do HIG, and then we have to input the amount of moles and the temperature, and then we can return. And so we have to do the dot product, NP dot, of the number of moles and our heat of formation at the normal initial temperature, 298 kelvins. And then we have to do plus our integrated heat capacity, which is the NP dot of N in our function delta H since IG at T minus delta H since IG at 298. So now to finish, we can actually calculate what our final temperature is going to be using our initial conditions, moles, and our feed, et cetera, et cetera. So we can define energy balance of V. It'll be a vector, and in this vector, it'll just be one component, which will be the temperature, the first and only component, and then we can return basically just the heat of formation at our initial moles at the initial temperature minus the heat of formation at with the final moles, the moles of the products, and our final temperature. I'm going to do HIG in feed, and then 298 minus HIG in products T. And so we can now use our root solver and input energy balance, and we can have some initial guess, which will be our initial temperature, 298 kelvins. And we get our answer. Our success was true, and we know that with our initial conditions, our initial amount of moles, after everything that we have set up and calculated, we know that the final temperature will be 1,461 kelvins. Thanks for watching.